Let's now discuss some topics about sources of sound. And we can talk about vibrating springs and air columns. We've already spoken about vibrating springs in chapter 15. So we can just use that material. We don't have to review over it again. All the same principles apply when we're talking about for sound. But we can look at air columns or tubes. So when we talk about air columns, can't spell columns, we're talking of some kind of tube. Now, there's two possibilities. You can have open on both ends, or you can have closed on one end, open on the other. Okay, so let's take a look at the open tube. Here we have a diagram of the waves inside of an open tube on both sides. Now, what the picture is depicting on the left-hand side is the air movement inside the tube. So you notice how the two edges are very far apart on the ends, and this is showing that there is a lot of air movement at the ends. And that makes sense because the air is moving in and out of the tube. But you get to a certain point and you get this node inside of the tube where there is no air movement. And so you have this standing wave with the air movements. Depending on where you are in the tube, depends on where the air is moving and where it's not. Now, this would be what we would consider the fundamental frequency. And so you notice that if I start here, I have one part of the wave and another part of the wave. So again, we have one wave fitting in a length of pipe. And so for our fundamental or first harmonic, we have the length of the tube is 1/2 the wavelength. And the frequency is going to be the velocity of the air in the tube divided by twice the length, or that's also lambda 1. Now for the second harmonic, you notice that you have two nodes inside the tube where there is no air movement, and when you look at the ends, there's a lot of air movement, and in the center there's a lot of air movement. So when we think about this air is oscillating back and forth, except for at this point there's no oscillation. In the center, the air is just moving back and forth. So for the second harmonic, the length of the tube is just lambda 2, and for our second harmonic, the frequency is just velocity divided by the length, and that's just twice frequency 1. The third harmonic, you can see how you have 3 nodes where there's no air movement, and yet you have these different regions where you have a lot of air movement. And here again you have the length is 3/2 lambda 3 for the third harmonic, and you have the frequency. Now this mimics, when we look at the formulas, this is basically, see if I can get an eraser here. This is basically like a string between two fixed points. Now, if we want to look at the pressure inside of the column, we can think about this as the center being 0, and the antinodes, or the heights, denote the magnitude of the pressure. And at the ends, where there's a lot of air movement, there is no pressure. But as you get to the node, the pressure increases so that it is a maximum at the node. And then the pressure will decrease to the other end so that there's no pressure and the air is moving freely. It's the same also when you look at the second harmonic. You have this area of no pressure, which exists in this part right here, where the air is moving the most, and the high pressure at these 2 points in the wave relate to where there is no air movement. And the same with the open on both ends for the third harmonic. So just remember that the equations are very much like a string fixed between 2 points. Notice that it's a half. You could say this is 2/2, which would be 1, 3/2 for the fourth harmonic. F4 is just 4F1, and the length is just going to be equal to 4 over 2 lambda 4, and that's just equal to 2 lambda 4. So this is the open tubes. Now let's take a look at closed tubes. And here we find that we can't really fit wavelengths in here like we did with the open tube, because there is never going to be air movement at the end. So that always has to be a node. So you notice that here we start with a wave, and then it gets reflected back. And we only can get a quarter of a wave in for the first harmonic. So the frequency is just equal to the velocity of the air in the closed end tube divided by 4L, which is just our lambda 1. Now, there is no way to fit a wave inside of this tube so that I can have a second harmonic. It would turn out to be that the ends would be open in some way. And then you'd have a point where it's no movement, something like so. And that can't happen. So there are no even harmonics with a closed tube. So our next harmonic, would be the third harmonic. And the third harmonic, the length of the tube is 3/4 lambda 3. And the frequency is just 3 times the velocity divided by 4 times the length. And then for the fifth harmonic, notice that the length of the tube is 5/4 times lambda of the fifth harmonic. So we have odd harmonics. That's the only thing that works. And notice that to figure out the fraction, you're always going to have 4 on the bottom. Okay. And the harmonic number goes with the lambda. So you notice that for the first harmonic, the length is 1/4 lambda 1. The length for a third harmonic is 3/4 times lambda 3. And the fifth harmonic is 5/4 times lambda to the fifth harmonic. If we wanted F7, that's just going to be 7 times frequency 1, and our length is going to be equal to, now it'd be the seventh harmonic, so following in this pattern, we would have 7/4 lambda to 7th harmonic. And again, with the pressure, we see how at the end of the tube, the air is going to be moving freely, so the pressure is 0. And at the end of the tube, we're going to have the highest pressure. This is for the first harmonic. For the second harmonic, again, the air is always going to be moving at the opening of the tube, and you're going to have the most pressure at the fixed end, but you're also going to have pressure somewhere in the tube, and you're going to have a node where there is a lot of air movement. There's a lot of air movement here in the tube where there's no pressure. No pressure. And the same with the third or the fifth harmonic. So these are the basic formulas for waves in a tube, and we'll be able to solve some problems on the homework based on these formulas. So just make sure you remember that the open tube can handle any harmonic, but the closed tube on one end can only handle the odd harmonics. That's the key. That's the trick to doing the problems in the homework.